Okay, so in today's video, we're actually going to be proving the following formula. So the integral from 0 to infinity of e raised to the negative x squared plus a squared divided by x squared dx is equal to the square root of pi divided by 2 multiplied by e raised to the negative 2a, for a can be some sort of real number. The methods and result will actually come out smoothly, and the work that we're going to show, there's going to be a lot of techniques, and there's going to be a specific subject specifically from differential equations that's going to be used to help prove this formula. So with that, let's actually get started. So what I want to do first is I want to define let I equals this formula again, or the integral from 0 to infinity of e raised to the negative x squared plus a squared divided by x squared dx. And then what I want to do now is I actually want to take the derivative of this integral in respect to a. So we can actually define I as a function in respect to a. So I of a, or in this case when we define the derivative, so I prime of a is equal to d over dA of this integral here, e negative x squared plus a squared divided by x squared dx. And then also, in other words, we can actually move the d over dA inside of the integral, so it can be rewritten as this. Let's see, e to the negative x squared plus a squared divided by x squared, then d, or this is supposed to be a bracket right here, then dx. Now when we take the derivative of the inside function in respect to a, so the only thing we're treating as a constant is the variable x, like when we're doing partial derivatives in this sort of sense. So when we take the derivative of this in respect to a, this is simply just 0, and this piece here is simply 2 times a divided by x squared. And we write this as so. Actually, well, in this case it's a negative being distributed, so it's supposed to be negative 2a divided by x squared of e to the negative x squared plus a squared divided by x squared dx. Okay. Now what I want to do now is I would actually want to take a look at inside of the exponent. Specifically just the one we're looking in the parentheses, nothing to do being multiplied with a negative. So what I want to do is I actually want to add a zero pair. In other words, I would like to add and subtract a 2a, so x squared plus a squared divided by x squared minus 2a plus 2a. And when I rearrange the terms, when I'm going to move the negative 2a so it's in front of the a squared divided by x squared, 2a plus a squared over x squared plus 2a. And if you take a look closely, the first 3 terms here, it actually forms a perfect square. In other words, we can actually rewrite this as x minus a divided by x, then plus 2a. And it works, so x times x is x squared, x times negative ax is just negative a. You do that a second time, so negative 2a, and then ax times ax, negative times negative, so it's positive, so a squared, x squared. So we can actually substitute this piece for here, and like so, negative 2a x squared e to the minus, and I'm going to put in brackets over here, x minus a over x squared plus 2a dx. Okay, all right, so far so good. What I can actually do now is I can actually, because there's a negative 2 here, I can just simply move that outside, so of the integral, so it's just negative 2 multiplied by the integral. and then a divided by x squared, then e, and if I want, and I can do this too. I can actually just because they shared the same base, I can separate it out. So what I can do is I can actually just rewrite this as minus x, x minus ax squared, then multiply by e, distribute the negative, so it's minus 2a dx. Okay. And now next what I want to do now is we're actually going to be adding another zero pair for this term here in particular. So when we rewrite this, I'll try my chair so I can squat a bit. We can rewrite this as -2, 0 to infinity, and I'm going to put in the braces or brackets. So this will be in parentheses 1 plus a x squared, then minus 1, close bracket, then e to the negative x minus x and square, then multiply by e to the negative 2a dx. And now because of this, we can actually split this into two different integrals. Specifically, when we have these two, when we have the e bases, we can just distribute to this term here and to this term as well. That's actually what I'm gonna be planning to do. So and because I'm doing that as well, I'm also going to distribute the -2 into this term here, just what I'm going to do with this term as well. So this is -2, the integral from 0 to infinity of 1 plus a over x squared, then e raised to the x minus a divided by x square e to the negative 2a dx, and then minus minus, so now we have positive, plus 2, then the integral from 0 to infinity of e to the negative x minus a divided by x square, then raised to the negative 2a dx. And now let's actually pay attention to this term for now, because I'm going to combine, since they have the same base, I'm going to combine with its exponents. So let me use my purple marker, and let's just focus on this term for now. So when we rewrite this, it's the same thing as 2 raised to the 2 times the infinity integral, excuse me, 2 times the integral from 0 to infinity of e to the negative x minus a divided by x square, then minus 2a. Let me put a bracket over here. Or now it's plus 2a in this sense, since we factor out a negative. So this 2a dx. Okay. So we actually established earlier that this is equivalent with this, but as earlier, it's also can be rewritten as the same as this piece right here. Let me draw my arrow. This piece is equivalent to this piece here in particular, this expression. So we can actually just substitute this for this expression here. So in other words, this is the same thing as 2 to the integral from 0 to infinity of e raised to the negative x square minus or plus a squared divided by x squared, then dx. But it's also interesting because this is the same thing as what we established as we set I is equal to this integral. So we can actually rewrite this as 2 times I, and then I'm going to write it as a function I of a. So when we rewrite this, let me first restate that I prime of a is equal to this integral here, And also because there's a e to the negative 2a where it's focusing, where it's integrating in respect to dx, this is just a constant, so I'm just going to move that outside. So this is negative 2 e to the negative 2a, and the integral from 0 to infinity of 1 plus a divided by x squared, then e raised to the x minus a over x squared dx, and then plus 2 times I to the a, and then I can subtract the 2 times I to the a to both sides, so then we get I prime of a minus 2 I of a equals this integral, like so. 2a 0 infinity 1 plus a x squared, and then e minus x minus ax, a over x, and then dx. And now this is this integral is simple because we can actually do a u substitution. So using my purple marker again, we're gonna let u equals this the inside of the exponent from e raised to this piece here. So it's just, let's see, u is equal to x minus a to the x. Then du is equal to 1. Then a over x is the same as a times x to the negative 1. So this is just negative 1 times a multiplied by x to the negative 2. So this is negative, so that turns into a positive. Then this is just a, and then x squared. And would you look at times dx of course. And looky, we have something that actually cancels out. So we have, we're going back to, well, actually I'll still use this again. And going back, we have negative 2 e to the negative 2a, and then we're changing variables so we have to change our bounds as well. So as x approaches 0, then 0 minus a over 0, so that's negative infinity, and then infinity, so it's infinity minus a divided by infinity, which is 0, so this is still infinity over here. And then when we substitute du, so 1 plus a over x squared, this cancels and this cancels, this will be substitute for du, and then e to the negative u square du. Now this is very interesting because this integral in particular this is the Gaussian integral. I actually covered a video on the Gaussian integral many months ago, so if you want to know how to evaluate this specific integral, I'm gonna link the video into my description for you guys to check it out. I'm not gonna show the work again a second time since, again, I already made the video. So if you wanna see how to calculate this specific integral, the video will be in the description. And we know, and because of that, we know that this specific integral is actually equal to the square root of pi. So this is rewritten as negative 2 e to the negative 2a, and then times the square root of pi. Okay, so now let me also put a little note right here that this is Gaussian integral, like so. Okay, and now rewriting everything we have. So we have I prime of a minus 2 times I of a is equal to negative 2 e to the negative 2a times the square root of pi. Okay, now this is very interesting. This is actually, now the next thing we're actually going to do is pay attention that this is actually a very special form. This is a differential equation. Specifically, this is known as a linear equation. The form of a first order linear equation in particular actually has the form and I'm gonna state this for dy dx in this case. So there's the form dy over dx plus p of x multiplied by y is equal to q of x. And then we also need to establish that we need to have an integrating factor, so defined as mu of x equals e raised to the integral of p of x dx. And that's what we're gonna do. So you just plug in your pieces with this form and then solve like a normal linear equation, not to be confused with a linear equation with the form y equals mx plus b. It's totally different. Do not get that confused. So now take a look at the pieces we have. So we have p of, in this case, it's supposed to be a. So p of a is equal to -2, and then q of a is equal to this piece. So I'm gonna move to the square root of pi next, right beside the -2. So -2 square root of pi e to the -2a. Okay. And now we need to calculate our integrating factor. So mu of a is equal to e raised to the integral of -2 dA, and that's simply just equal to e to the -2a. So now we have that, so we have to multiply our integrating factor to both sides of the equation. So in other words, this is written as I prime of a multiplied by e to the -2a, then minus 2 I of a multiplied by e to the -2a, which is equal to, multiply this is -2e to the minus 4a, and multiply by the square root of pi. And this actually comes out nicely because this is actually its product rule. So in other words, this is the same thing as rewriting as d over dA of I of a multiply its integrating factor e to the -2a, and then equals this -2 4a square root of pi. And now all that's left is to take the integral to both sides. If you want to check, you can actually take the product rule of this, and it actually comes down to the same as this. I of a e to the -2a, its product rule is I prime of a multiplied by this, and then plus I of a multiplied by the derivative of e to the -2a is minus 2a e times e to the -2a. And now all that's left is we gotta take the integral of both sides in respect to dA, of course. And then when we take the integral of this, it just cancels out. So the d over dA and then the dA just cancels. So all that's left is just the inside. So it's just I of a e to the -2a, which is equal to this integral here. So this is let's see. So this is we can move the -2 times e to the pi over square root of pi to outside of the integral, and all we're left with is just integrating e to the -4a, which it's simply just do a u sub. So it's just -1 over 4 times e to the -4, and negatives cancel out, so it's simply just the square root of pi divided by 2, then e to the -4. And now, and then don't forget, because this is still an this is an indefinite integral, so we have to add a constant. So we'll call it c, and then we can just divide e to the -2a to both sides. It's just simply we get I sub a is equal to minus 4a, and then plus, so that will be the square root of pi divided by 2 multiplied by e to the -2a, then plus c times e to the 2a. So, okay, so now all that's left is we need to solve for constant c. So let's actually just use the basic case. A is equal to 0. So if we let a equal 0, then I sub 0 is equal to the square root of pi divided by 2, e to the negative 2 times 0, then plus c times e to the 2 times 0. And in other words, that's the same thing as the square root of pi divided by 2, then plus e to the 0 is just 1, so plus c. And note that when we're plugging a is equal 0, we're plugging to this equation here in particular. So let me write that I of 0 is equal to the integral from 0 to infinity of e to the negative x squared plus 0 squared divided by x squared, then dx. In other words, this is 0 to infinity of e to the negative x squared. And that's actually the Gaussian integral again, but it's actually half its area since it's from 0 to infinity, so it's just the square root of pi divided by 2. So now we have that I of 0 is equal to the square root of pi over 2, and set that equal to this, square root of pi divided by 2 plus c, where we obviously know from just simple algebra c is equal to 0. And therefore we can actually conclude that the function I, or in this case, rewrite this integral, 0 to infinity, can you see this integral? Yeah, you can. Okay, cool. Of e to the negative x squared plus a squared divided by x squared dx is equal to the square root of pi divided by 2 times e to the negative 2a. Like so. Let me circle this in purple before I end the video. Boom. We just proved it. That's awesome, right?